Light, the cosmic speed limit, defines our understanding of the universe. It moves at nearly 300,000 kilometers per second, a pace so astonishing that it shapes the very laws of space and time. Yet, as vast as this velocity seems, the question lingers, is light truly the ultimate barrier? Beyond this radiant frontier lies a realm of speculation, of physics stretched to its limits, and of possibilities that defy imagination. What would it mean to cross that invisible threshold? What consequences would unfold if matter, energy, or even information could surpass light's dominion? Tonight, we embark on a journey into the depths of theoretical physics, exploring what lies beyond the speed of light. With precision, clarity, and awe, we shall venture into concepts that challenge the very structure of reality itself. With that said, let us begin. The speed of light is not simply fast, it is foundational. According to the framework of relativity, light speed is the defining constant of the universe. Space and time themselves are woven around it. No matter how one moves, whether drifting slowly or accelerating to near relativistic velocity, light's pace remains unchanged. This invariance transforms it from a mere measurement into a cosmic law. To approach this boundary is to encounter distortions of perception. A spaceship nearing 90% of light speed would experience time dilation, where moments stretch and seconds tick slower compared to those at rest. Distances contract, objects flatten, and energy requirements soar exponentially. Each percentage closer demands incomprehensibly more energy, creating a wall of impossibility. This barrier is not built from matter, but from the geometry of spacetime itself. Yet, the curiosity of science compels us to ask: is this barrier absolute, or is it only apparent from our perspective inside the universe? Could the laws we understand merely describe the limits of our observational domain, while deeper truths lie hidden beyond? If light speed is a threshold, then what happens if something, or someone, were to cross it? Would causality unravel? Would time reverse? Or could entirely new frameworks of existence reveal themselves? Thus, the speed of light is more than a number. It is the keystone of reality, anchoring motion, communication, and causality. But every wall invites speculation about what stands on the other side. The notion of traveling faster than light is a theme of both scientific exploration and human imagination. To exceed this boundary would mean breaking free from the chronological chains of cause and effect, for events beyond light speed no longer obey conventional order. The universe, as we know it, would bend into paradox. Messages could arrive before they were sent, travelers could appear at destinations before their departure, and the distinction between past, present, and future might dissolve entirely. In theoretical physics, superluminal travel often invokes concepts such as tachyons, hypothetical particles that always move faster than light. Tachyons, if they exist, would never slow down to sublight speeds, instead, they would forever inhabit a realm inaccessible to us. Their existence would suggest a mirror-like layer of physics, a domain where the ordinary rules of time do not apply. However, despite decades of searching, no experimental evidence for tachyons has ever surfaced. They remain shadows of mathematical speculation. Another pathway toward surpassing light involves manipulating spacetime itself. Rather than moving through the cosmos faster than light, what if the cosmos moved around you? Concepts such as warp drives or spacetime bubbles propose this very idea. Contracting space in front of a vessel while expanding it behind. In this way, the craft itself never exceeds light speed locally, but the distance it crosses can be traversed faster than light would otherwise allow. These concepts remain theoretical, bound by energy requirements that border on the unimaginable. But they illustrate the deep yearning to pierce the horizon of possibility. For if one could move beyond light speed, not only the stars but entire galaxies might come within reach. The barrier is not just physical, it is philosophical, for to surpass it would mean stepping into an unknown reality where even the arrow of time might fracture. Surpassing light speed introduces a profound consequence, the collapse of causality. In the subliminal world, events follow sequence, cause leads to effect, and past builds into future. But faster-than-light travel disrupts this order. Observers in different reference frames could disagree on the sequence of events, creating paradoxes that strain reason itself. Imagine a signal sent faster than light to a distant star system. To one observer, the message leaves first and arrives second. To another, moving at a different velocity, the message might appear to arrive before it was sent. This reversal of order is not a mere illusion but a genuine contradiction within the structure of spacetime. It challenges the very bedrock of logic. How can an effect precede its cause? How can the consequence come before the action? This phenomenon is known as the causality violation, and it is why many physicists argue that faster-than-light communication or travel may be forbidden at the deepest levels of reality. Allowing such paradoxes could unravel the universe's consistency, creating feedback loops where events cause themselves, or where the future dictates the past. Yet, paradoxes also signal the frontier of knowledge. They force us to question whether our understanding of time is complete. Perhaps causality, as we know it, is not fundamental but emergent. Perhaps beyond the light barrier exists a higher framework where paradox is no paradox at all, merely the natural order of a reality we cannot yet perceive. Thus, the paradox of causality serves both as a warning and as an invitation. It cautions us about the dangers of venturing beyond light speed, yet it tempts us with the possibility that time itself may be a construct waiting to be transcended. As one accelerates toward the speed of light, a strange and unforgiving reality emerges. Energy demands grow without limit. A spaceship moving at 50% of light speed consumes an extraordinary amount of fuel, but to push it further, to 99%, the energy requirements multiply into staggering proportions. At 99.9%, the energy needed is beyond the grasp of even the most advanced civilizations imaginable. To actually reach light speed itself, the energy required is infinite. This phenomenon is not a technical limitation, it is woven into the fabric of physics. The closer matter moves toward the cosmic speed limit, the greater its relativistic mass becomes. With more mass, greater energy is needed to push further, creating a cycle that spirals toward impossibility. It is a wall built not of metal or stone, but of mathematics and the very definition of motion. Some theories suggest that bypassing this wall would demand exotic energy forms, such as negative energy or hypothetical constructs like dark energy manipulation. Concepts such as wormholes or warp drives rely heavily on such ideas. But even these speculative routes do not allow one to truly exceed light speed, they merely bend the playing field, adjusting space-time itself so that distances shrink rather than speeds increase. Thus, the energy wall stands as one of the greatest obstacles to superluminal dreams. It ensures that faster-than-light travel is not a simple matter of better engines or more efficient fuels, but a question of rewriting physics itself. If there is a way beyond, it will not be through brute force but through discovering principles that lie hidden, perhaps within dimensions or forces we have yet to uncover. The wall of energy is daunting, yet it also beckons with the promise that behind it may lie the keys to a new universe of possibilities. Among the most fascinating ideas in physics is the proposal of tachyons, particles that, from the moment of their creation, move faster than light. Unlike ordinary particles, tachyons could never slow down to subliminal speeds. Their existence, if real, would mean that faster-than-light motion is not forbidden everywhere, but instead belongs to a hidden class of phenomena we simply cannot yet detect. Tachyons arise naturally in certain mathematical formulations of quantum field theory. They occupy a strange niche. Their energy decreases as their speed increases. In other words, the faster they go, the less energy they possess, a reversal of the rules that govern everything we know. This bizarre trait makes them unstable in most physical models, often signaling that the theory itself may be incomplete. If tachyons exist, they would interact with time in ways that defy comprehension. Observers might detect them arriving before they are emitted, their presence rewriting the order of events. They would live in a domain where cause and effect are inverted, a universe parallel to ours yet forever disconnected by the laws of relativity. No evidence for tachyons has ever been observed, and many physicists consider them mathematical artifacts rather than physical realities. Still, the notion of tachyons serves as an intellectual bridge to imagining what lies beyond light speed. They challenge us to envision a mirror world governed by reverse logic, where our limitations dissolve and new rules reign. Even if tachyons are never found, the thought of their existence keeps alive the possibility that nature hides secrets in realms forever beyond the luminous boundary of light. If faster-than-light travel through conventional motion is forbidden, perhaps the answer lies not in breaking the limit, but in bending the rules of space-time. Wormholes, theoretical tunnels linking distant regions of the cosmos, offer precisely this kind of escape from the ordinary. By passing through a wormhole, one might arrive light-years away in an instant, not by exceeding light speed, but by taking a shortcut through the fabric of reality. The mathematics of general relativity allows for such constructs, at least in theory. Visualize space as a sheet of paper. 2 points far apart can be brought together by folding the paper, then piercing through. A wormhole functions much like that fold, collapsing immense distances into traversable bridges. Unlike tachyons, wormholes do not require particles to exceed light speed, they simply reshape the geometry so that the journey is effectively instantaneous. The challenge lies in stability. Wormholes, if they form naturally, are believed to collapse almost instantly, snapping shut before anything can cross. To keep them open, theoretical physics demands the presence of exotic matter with negative energy density, something never observed but faintly hinted at in quantum effects such as the Casimir vacuum. Even if such matter could be harnessed, engineering a wormhole on cosmic scales is beyond our comprehension of technology. Yet the implications are staggering. Wormholes, if real and navigable, would redefine not only travel but causality itself. They could serve as gateways across the galaxy or even through time. Some theories suggest wormholes might already exist, hidden within the dark voids of space, waiting like unseen portals. Their discovery would mean that light speed is not the ultimate limit after all, but merely one route among many across a universe far stranger than we currently imagine. If wormholes are too unstable to be practical, another bold proposal emerges: the warp drive. Instead of moving a vessel faster than light, the warp drive bends the very fabric of spacetime around it. Imagine placing a ship inside a bubble of distorted reality. Space in front of the vessel compresses, while space behind it expands. The ship itself never moves locally faster than light, but the bubble carries it across vast cosmic distances at effective superluminal speed. This concept, most famously associated with the Alcubierre metric, is rooted in solutions to Einstein's equations. On paper, it is allowed by the mathematics of relativity. The implications are astonishing. Journeys to distant stars that would take tens of thousands of years by conventional means could be reduced to days or even hours. Within the warp bubble, passengers would feel no acceleration, no crushing forces, no violation of the laws of physics as they know them. Yet the warp drive faces monumental challenges. The first is energy. To generate such a bubble would require amounts of energy rivaling the mass energy of entire planets or stars, unless some yet unknown loophole reduces the cost. The second challenge is exotic matter. Like wormholes, warp drives appear to demand negative energy density, something not found in everyday physics. A third issue lies in causality. Warp bubbles may allow faster-than-light travel but also open the door to paradoxes, creating closed time-like curves where time itself loops backward. Even with these hurdles, the warp drive remains a tantalizing vision. It represents a bridge between theoretical physics and the dreams of interstellar travel. Whether it is a mathematical curiosity or a genuine blueprint for the future, it forces us to consider a universe where faster-than-light motion might be achieved not by breaking the rules, but by reshaping them. Beyond the realm of physical objects, another question arises: can information itself move faster than light? According to relativity, the answer is no. Information, like matter, is bound by the luminous limit. This rule preserves causality and ensures that no message can outrun the cosmic clock. But in quantum mechanics, the situation grows more mysterious. Consider entanglement, the eerie connection between particles separated by vast distances. Measure one particle, and its entangled partner instantly reflects the result, no matter how far apart they are. To many, this appears to be faster than light communication. Yet experiments and interpretations insist otherwise. While correlations emerge instantaneously, no usable information travels between the particles. The universe preserves its prohibition, even in the face of quantum strangeness. Still, the existence of entanglement suggests that the speed of light may not be the ultimate arbiter of all interactions. Instead, it may govern the transfer of measurable information, while deeper layers of reality operate under different rules. Some theories suggest that beneath spacetime lies a more fundamental order, a web of connections unconstrained by distance or speed. In this hidden architecture, what we perceive as limits are but emergent properties of the visible universe. If this is true, then perhaps information, true, manipulable, meaningful information, might one day find a way to move beyond light speed. The implications would be extraordinary: instantaneous communication across galaxies, messages from one end of the cosmos to the other without delay, even the possibility of accessing knowledge from futures yet to unfold. The horizon of information is not merely about speed. It is about redefining what knowledge and connection mean in a universe larger and stranger than we can presently conceive. At the core of the faster-than-light debate lies time itself. For time is not an independent river flowing regardless of our actions, it is tied intimately to the speed of light. If one could surpass this boundary, time would cease to behave as we expect. A traveler moving faster than light could, from some perspectives, arrive before their journey began. In certain frames of reference, they might appear to reverse time, stepping into a past that others still call the future. This is the essence of superluminal paradox. It dissolves the arrow of time, the simple forward march from cause to effect that structures all experience. Physicists have wrestled with this notion for decades. Some argue that superluminal travel must be impossible precisely because it creates contradictions. Others counter that our understanding of time may itself be incomplete. Perhaps what we call the past and the future are not fixed, but fluid, with superluminal motion revealing their deeper unity. There are even suggestions that time, as we perceive it, is not fundamental at all but an emergent property of deeper laws. If so, surpassing light speed could be less about breaking causality and more about stepping into a realm where causality does not apply. In such a domain, past and future might coexist, not as separate realities but as facets of a single cosmic tapestry. Thus, the superluminal frontier is not merely about velocity. It is about the essence of time. To cross beyond light speed may be to discover that time itself is not a universal constant, but a shadow of something greater, a structure that collapses when pushed to its limits, revealing a reality where beginnings and endings are indistinguishable. One of the most intriguing ideas about what might exist beyond the speed of light is the possibility of entire alternate realities. Parallel universes, layered beside our own, hidden from view by the very limits of motion and information. If light defines the horizon of our universe, then perhaps crossing that boundary means stepping into another. The multiverse hypothesis suggests that our cosmos may be only one of countless universes, each with its own laws, constants, and perhaps even different versions of space and time. Faster-than-light travel could act as the bridge between these realms. Imagine a traveler pushing through the barrier, not simply moving faster than light within our universe, but falling out of it entirely into another layer of reality. To us, this would appear impossible, but in another framework, superluminal speed might represent motion across universes rather than through them. Some theories of quantum mechanics support this vision, suggesting that every possibility spawns a branching universe. Others, tied to cosmology, propose that inflation may have generated infinite bubble universes, each isolated by distances light could never cross. Yet, if superluminal phenomena are possible, those barriers might not be absolute. The faster-than-light frontier may not only reveal new regions of our universe, but other universes altogether. If so, the question deepens: what would it mean to travel not merely across space, but across realities? What would physics look like in a universe where light speed differs, or where causality follows alien rules? Beyond light speed, we may not only find the stars, we may find other universes waiting in the shadows of existence. Black holes represent nature's most extreme laboratories, where space-time bends so completely that even light cannot escape. To approach their event horizons is to approach the very definition of the speed of light barrier. Inside, physics as we know it breaks down, and speculation becomes inevitable. Could black holes conceal the key to surpassing the cosmic limit? Theories abound that black holes might connect to other parts of the universe, or even other universes, through wormhole-like structures. These hypothetical Einstein-Rosen bridges suggest that the singularity at a black hole's heart could act as a gateway. A traveler falling past the event horizon might, in principle, emerge elsewhere, perhaps faster than light could travel through ordinary space. The challenge lies in survivability. The tidal forces near singularities are immense, stretching and tearing matter apart in a process often called spaghettification. Yet if there exist rotating or charged black holes, the mathematics implies that their interiors might harbor hidden passageways, stable long enough to permit traversal. These solutions are highly speculative, but they open the door to envisioning black holes as more than destructive abysses. If black holes do serve as shortcuts, they redefine the speed of light limit. Instead of brute force acceleration, one might use the universe's most extreme objects as natural gateways. The cost, however, would be profound. The traveler risks not only destruction but also the possibility of emerging into an entirely different realm of physics. Beyond light speed may not lie open stars, but the unknowable heart of darkness. At the microscopic level, nature behaves with a freedom that defies classical logic. In quantum mechanics, particles sometimes cross barriers that should be impassable. This phenomenon, known as quantum tunneling, allows electrons to slip through energy walls, enabling the very processes that fuel stars and power life. Could tunneling also provide clues about surpassing light speed? In certain experiments, particles appear to tunnel faster than light, vanishing from one location and reappearing elsewhere in less time than light would need to travel the same distance. These results are hotly debated, for most interpretations argue that no usable information actually moves faster than light. Still, the mere suggestion that particles can behave in ways that mimic superluminal motion raises profound questions. Perhaps light speed is not a hard wall at every scale, but an emergent property of large systems. In the subatomic world, where uncertainty rules, faster-than-light phenomena may flicker in and out of existence, hidden within the statistical haze of quantum events. If so, then our universe may already permit superluminal processes, we simply lack the tools to harness them. Quantum tunneling also hints at a deeper truth: what we perceive as barriers may not be barriers at all, but probabilities waiting to collapse. Faster-than-light travel might therefore not require brute force energy or exotic spacetime manipulation, but clever exploitation of quantum rules. If we ever master the art of guiding tunneling on macroscopic scales, we may find that light speed was not a limit after all, but a veil concealing stranger possibilities beneath. If space and time as we know them impose insurmountable limits, perhaps the answer lies outside of them altogether. The concept of hyperspace, theoretical dimensions beyond the familiar three of space and one of time, offers a radical possibility. What if faster-than-light travel is not motion within our universe, but a passage through higher dimensions where light speed does not apply? Mathematics already entertains such ideas. String theory, for example, proposes that additional dimensions curl tightly beyond perception, hidden within the smallest scales of reality. In these extra dimensions, the constants of physics might differ, and the restriction of light speed may not exist. A vessel capable of entering hyperspace could potentially bypass the constraints of ordinary spacetime, emerging elsewhere in our universe in moments. Science fiction often portrays hyperspace as a vast ocean, a parallel realm through which ships sail faster than light. While speculative, the imagery captures an essential truth: to escape light speed, one must leave behind the stage on which light is the measure. The higher dimensional landscape could be filled with shortcuts, unseen connections, and pathways invisible to us within the flat projection of four-dimensional space-time. If hyperspace exists, then perhaps faster-than-light travel is not about breaking rules but accessing new ones. Yet this idea raises unsettling questions. What dangers might lurk in dimensions we cannot perceive? What beings or phenomena might dwell in the unseen fabric? Hyperspace may not simply be a highway across the stars but an entirely alien realm, with its own laws, its own dangers, and its own mysteries. Among the most fascinating relics of theoretical cosmology are cosmic strings, hypothetical defects in spacetime, thinner than an atom yet stretching across the universe like filaments of unimaginable energy. Formed in the earliest moments after the Big Bang, these structures could warp spacetime so severely that they act as shortcuts across vast distances. If two cosmic strings pass near one another, the distortion of spacetime could create a lensing effect so powerful that it allows superluminal shortcuts. A spacecraft maneuvering near such a structure might effectively leap across light-years in less time than light itself would take. Unlike warp drives or wormholes, cosmic strings may not require the creation of exotic matter; they might already exist, waiting to be discovered. Yet they are elusive. No observational evidence has yet confirmed their presence, though astronomers have searched for the gravitational signatures they would produce. If they do exist, they may be scattered sparsely across the cosmos, hidden in the dark expanses between galaxies. Encountering one could be both a tremendous opportunity and a colossal danger, for the gravitational forces surrounding them would be catastrophic if approached recklessly. Cosmic strings illustrate a broader truth. The universe may already contain natural phenomena capable of enabling motion beyond light speed. Rather than inventing impossible technologies, perhaps we need only to uncover the relics of the cosmos itself, structures born in the fires of creation, silent witnesses to the birth of reality, and potential gateways to faster-than-light travel. When we speak of light speed, we often forget its most profound implication: it defines what we can see. The universe is not infinite in our vision, even if it is infinite in size. Beyond a certain distance lies the cosmic horizon, the boundary beyond which light has not yet had time to reach us. At present, this horizon sits at about 46 billion light-years, a sphere enclosing all we can observe. Faster-than-light travel would mean breaching this horizon. It would allow us to step beyond the curtain of the observable universe, into regions forever hidden from our telescopes. What would we find there? Entire galaxies uncounted, perhaps governed by variations of the same physics, or regions where the laws themselves diverge. Beyond the horizon, the universe is uncharted, unseen, and unknowable by any means bound to light speed. Crossing it would not only expand our map of the cosmos but redefine our place within it. We would no longer be confined to a single observable patch, but explorers of the greater whole. Perhaps we would discover that our universe is only a fraction of a vast and endless ocean, stretching infinitely in all directions. Or perhaps we would encounter boundaries, edges, or transitions into domains where even the concept of space loses meaning. To speak of faster-than-light travel is not merely to imagine speed, it is to imagine expanding the limits of existence itself. Beyond light lies not just distance, but an entirely new universe, waiting to be revealed. The speed of light is not simply a number on a chart, it is the stitching that holds spacetime together. To exceed it might not just challenge physics, it could fracture the very structure of reality. Relativity tells us that as objects approach light speed, spacetime itself bends and twists, protecting causality from being violated. But what if something forced its way past this threshold? Some theories suggest that exceeding light speed would tear open rifts in spacetime. These rifts might behave like miniature wormholes, unstable tunnels leading to unknown regions. Others argue that superluminal travel could release immense bursts of radiation, collapsing the very field of energy around the traveler. To break the fabric is to risk unraveling the order of the cosmos, creating zones of chaos where familiar laws no longer apply. Yet, in these dangers lies potential discovery. Perhaps faster-than-light motion does not destroy spacetime but reveals hidden layers of it, like peeling back the surface of a tapestry to reveal intricate patterns beneath. These patterns might represent deeper dimensions, latent structures we cannot perceive at ordinary speeds. Breaking spacetime could expose the machinery of the universe, the framework upon which reality is built. If so, then faster-than-light travel would not simply be about exploration, it would be about exposing truths that spacetime conceals. To move beyond light speed might mean to look directly into the engine of existence itself. But such a step would come with peril, for once the veil is pierced, we may never again view the cosmos in the same way. Dark energy, the mysterious force driving the accelerated expansion of the universe, may hold keys to the faster-than-light question. While ordinary matter and energy are bound by light speed, dark energy appears to act on spacetime itself, stretching it at scales far beyond human comprehension. Galaxies drift apart faster than light can bridge their growing separation, not because they move through space, but because space itself expands. This reveals an important distinction: motion within spacetime is limited by light speed, but spacetime itself seems to obey no such restriction. If dark energy can accelerate expansion beyond the luminous limit, perhaps it can be harnessed to create superluminal pathways. The concept of warp drives draws heavily from this idea, contracting and expanding regions of spacetime by manipulating energy fields. Yet dark energy remains profoundly enigmatic. It is invisible, detectable only through its effects on cosmic expansion. Its nature is unknown. It may be a property of the vacuum itself, a dynamic field, or something even stranger. To master dark energy would mean mastering the very engine of the universe's growth. If such mastery could bend spacetime at will, light speed would cease to be a prison and become merely one option among many routes through reality. But there is a darker side. Harnessing dark energy might destabilize spacetime on catastrophic scales, unraveling galaxies or even the universe itself. Faster-than-light travel through such means could come at the ultimate cost. It forces us to ask, is surpassing light speed worth tampering with the very force that shapes the cosmos? The potential rewards are vast, but so too are the risks. To understand what might exist beyond light speed, we must look backward, to the earliest moments of the universe. In the first fractions of a second after the Big Bang, the cosmos expanded faster than light in a process known as inflation. Space itself stretched at an exponential rate, pulling regions apart before light could connect them. This was not a violation of relativity, for again, it was not objects moving faster than light, but space expanding. If the early universe could outrun light, perhaps echoes of that expansion still exist, waiting to be discovered. Inflation may have left behind relics, subtle patterns in the cosmic microwave background, or hidden structures in spacetime that reflect its superluminal past. These relics could serve as natural gateways, regions where spacetime remains stretched or folded, creating shortcuts that we might one day exploit. Some cosmologists even argue that inflation never truly ended, that it continues in distant regions of the multiverse, creating new universes at scales beyond our comprehension. If this is true, then faster-than-light expansion is not a rare event but a fundamental property of reality itself. To access it would mean stepping into the very mechanism that births universes. Thus, the early universe whispers a profound truth. Faster-than-light processes have already shaped everything we see. The challenge is not whether they are possible, but whether we can ever learn to touch them. To do so would mean harnessing the same forces that created the cosmos, a power at once awe-inspiring and incomprehensibly dangerous. Time and speed are often thought of as partners, but they are not identical. The arrow of time, the reason we remember the past but not the future, arises not from light speed, but from entropy, the tendency of systems to evolve toward disorder. If faster-than-light travel becomes possible, it may not only distort motion but also challenge entropy's dominance. Imagine a vessel exceeding light speed. To one observer, its journey unfolds forward, while to another, it may appear reversed. Yet entropy still increases in each frame, preserving its grip even across contradictory timelines. This raises a profound question. If time order is relative at superluminal scales, could entropy itself be manipulated? Could faster-than-light processes allow the engineering of systems where entropy decreases, reversing decay, restoring order, even reviving what has been lost? The second law of thermodynamics is considered unbreakable, but relativity already showed us that time is flexible, dilated by motion and gravity. If entropy is tied to time, then perhaps the arrow we take for granted is not universal but conditional. Beyond light speed, the very distinction between cause and effect blurs. Might the same happen to the march of disorder? Some physicists argue that entropy defines reality more strongly than light speed, and that even if faster-than-light travel were achieved, entropy's arrow would remain unbroken. Yet others speculate that surpassing the cosmic limit may uncover deeper frameworks, where entropy is not a law but a local tendency, one that can be reshaped. The possibility is staggering. Faster-than-light travel may not only conquer distance but open the door to rewriting time itself. If messages could travel faster than light, the consequences would be as transformative as interstellar ships. Communication would no longer be bound by the slowness of light years. Civilizations separated by galaxies could converse instantly. Networks could span the cosmos, information flowing freely between stars. But with this power comes danger. The collapse of causality, introduced earlier, becomes a practical nightmare when tied to communication. A message sent faster than light could arrive before it was sent, creating paradoxes. A warning of disaster could arrive before the event occurs, prompting actions that prevent the disaster, negating the original reason for the message. These loops of logic spiral into contradictions, threatening the stability of history itself. Military applications add further peril. Instantaneous communication would render current systems of strategy and defense obsolete, allowing information to be weaponized in ways that bypass distance and delay. Worse, faster-than-light communication could allow adversaries to manipulate causality deliberately, sending signals into the past to change outcomes before they occur. The battlefield of tomorrow might not be fought in space or time but in causality itself. Yet the temptation is overwhelming. If a civilization ever cracks superluminal communication, it would wield a power equivalent to rewriting the cosmic script. Entire galactic societies could operate as single entities, distance dissolved into irrelevance. Knowledge, culture, and history could spread instantly, forever altering the pace of evolution. The dangers are vast, but so too is the potential. Faster-than-light communication is not just about talking faster, it is about reshaping the very logic of reality. Modern physics rests on the Standard Model, a framework that explains the known particles and forces of the universe. But even this elegant structure is incomplete. It does not explain dark matter, dark energy, or gravity's quantum nature. Some researchers speculate that hidden fields, beyond the Standard Model, may hold the secret to superluminal phenomena. These hypothetical fields could interact with spacetime in ways unknown to us. Just as electromagnetism carries photons at light speed, perhaps another field exists where carriers move faster, invisible to our instruments. If we could couple with such a field, faster-than-light travel or communication might become possible. Theories of supersymmetry, extra dimensions, and grand unification all suggest that physics has layers we have not yet uncovered. Within those layers, the speed of light may be less fundamental than it seems, merely the limit of our visible sector of reality. Other domains could harbor different constants, different barriers, and even different definitions of motion. If faster-than-light fields exist, they may already be influencing our universe subtly. Perhaps dark matter is not just unseen mass but the residue of interactions in a superluminal domain. Perhaps gravity itself leaks from faster-than-light processes, weak in our universe because most of its influence lies elsewhere. Unlocking these mysteries could reveal that the speed of light is not a universal constant but a local rule, one that can be bypassed by stepping into physics beyond our current grasp. In nuclear reactors, a haunting blue glow surrounds submerged rods of radioactive material. This glow is not mystical, it is Cherenkov radiation, the result of charged particles moving through water faster than light does in that medium. While nothing can exceed the universal speed of light in a vacuum, light slows in materials such as water or glass. When a particle outruns light's reduced speed there, it emits the characteristic glow, like a sonic boom of photons. Cherenkov radiation demonstrates that faster than light can exist in limited contexts. It is not faster than light in a vacuum, but it reveals that when the conditions of the medium change, the effective limit shifts. This provides a powerful clue. Perhaps the universal speed of light is not absolute, but context-dependent. If one could alter the properties of spacetime itself, lowering light's velocity locally, then surpassing it might become feasible without ever violating relativity. The glow of nuclear reactors may, therefore, be more than a laboratory curiosity. It may be a miniature model of what lies beyond light speed, particles escaping the usual order, creating new phenomena in their wake. If technologies could one day manipulate the medium of spacetime, crafting regions where light's constant bends to our design, the path to superluminal travel could open. Thus, the eerie blue radiance of Cherenkov light is not merely a sign of radiation, it is a whisper of possibility, hinting that even the cosmic speed limit might not be as unyielding as we once believed. Long before the equations of relativity, civilizations dreamed of transcending distance instantly. Ancient myths spoke of gods who traversed the heavens in a single stride. Folklore across cultures describes beings who outran light, crossed worlds in an instant, or spoke to mortals from across the stars without delay. These stories reflect a timeless yearning to break free from the barriers of time and space. In modern times, literature and cinema have transformed these myths into visions of hyperspace jumps, warp drives, and instantaneous portals. While scientists debate equations, storytellers imagine the consequences: galactic empires bound together by faster-than-light networks, explorers reaching distant realms, or civilizations collapsing under the paradoxes of time loops. These cultural expressions reveal more than fantasy, they highlight the psychological pull of surpassing the luminous limit. For humanity, faster-than-light travel represents ultimate liberation. It is the promise of endless discovery, the undoing of cosmic loneliness, the chance to explore without boundary. Yet it is also a source of fear. What might we unleash by tampering with time, causality, and the fragile laws that sustain order? The enduring fascination with superluminal speed shows that the question is not merely scientific but existential. It is tied to our identity as explorers, storytellers, and seekers of meaning. Physics provides the rules, but imagination asks, what if the rules can bend? And it is within this dialogue, between science and dream, that the search for what lies beyond light speed continues. Another perspective arises from digital thought, the possibility that our universe itself is a simulation. If reality is a vast computational construct, then the speed of light may not be a cosmic law, but a processing limit, a maximum refresh rate encoded into the system. In this framework, faster-than-light phenomena would be akin to breaking through the rules of a simulation. Just as hackers exploit flaws in computer code to bypass restrictions, perhaps the universe has glitches that allow motion or communication beyond the speed of light. Some theorists argue that quantum entanglement already resembles such a glitch, an instantaneous correlation across vast distances that seems to ignore spacetime. If our universe is a simulation, the implications are staggering. Faster-than-light travel might simply require accessing hidden commands or deeper layers of the program. The cosmic speed limit would no longer be the ultimate barrier, but a safeguard designed to preserve stability. Surpassing it could reveal the source code of reality, exposing levels of existence beyond our perception. This idea, while speculative, reframes the question of light speed. Instead of asking whether nature allows faster motion, it asks whether our version of nature is complete. To break the light barrier might mean stepping outside the visible rules and peering into the machinery that runs the cosmos. Whether metaphor or truth, the simulation hypothesis expands the frontier of imagination, showing that what lies beyond light speed may not only be physics, it may be reality itself. As the universe expands, galaxies drift ever farther apart. Beyond a certain threshold, they recede faster than light, not by moving through space, but because space itself stretches. To us, these galaxies slip beyond the cosmic horizon, becoming forever invisible. Their light, no matter how fast, can never catch up. In effect, they are lost to us, erased from the observable cosmos. This phenomenon already proves that faster-than-light separation is real in a cosmic sense. While no single galaxy breaks the rules of relativity, the fabric of spacetime creates conditions where entire regions of the universe are permanently beyond reach. To glimpse them again, we would need faster-than-light travel. Only then could we bridge the gulf and recover the galaxies vanishing over the horizon. What would these lost regions contain? Perhaps structures of breathtaking scale, clusters of galaxies larger than anything we have yet mapped. Perhaps entirely new forms of matter, born under different conditions. Or perhaps regions where physics itself took a different turn, where constants vary, and reality is written in an unfamiliar script. Each galaxy lost to the horizon is a question unanswered, a mystery sealed by light's finite pace. To break the light barrier would be to reclaim these unreachable realms. It would be to rejoin a universe that constantly slips beyond us, to expand our vision from a bubble into infinity. The cosmic horizon is not merely a boundary of sight, it is the line dividing what we know from what we cannot yet imagine. Beyond light speed lies not only speed itself, but the return of the lost. If faster-than-light travel is ever to move from theory to practice, new engines must be conceived, machines that do not merely burn fuel, but manipulate the universe itself. Physicists have proposed several radical designs, each stretching imagination as much as physics. One is the antimatter drive. By annihilating matter and antimatter, such an engine would release pure energy, orders of magnitude more powerful than nuclear fusion. While still bound to sublight speeds, antimatter propulsion might push vessels close enough to the light barrier that superluminal techniques, warp bubbles or wormholes, become feasible. Another is the black hole drive, in which a miniature black hole radiates Hawking energy, powering a craft as it moves. If controllable, it could produce staggering thrust. Others imagine engines that manipulate quantum fields directly, creating thrust not by reaction mass but by tapping into the vacuum of space. Perhaps the boldest proposals are not engines at all, but mechanisms for altering space-time. Instead of moving a ship, the ship moves reality around it, bending the rules of geometry. These concepts, warp drives, Alcubierre bubbles, wormhole stabilizers, are less machines than cosmic tools, requiring mastery of energies and dimensions beyond anything we know. These engines, though speculative, represent more than fantasy. They are exercises in possibility, blueprints of a future where faster-than-light travel is not myth but engineering. If we can dream the engines, perhaps one day we will build them. And if built, they will not just propel ships, they will propel us into the unknown. If faster-than-light travel is possible, then another question arises: where are the civilizations who have already mastered it? The universe is ancient, billions of years old. If even one civilization had learned to surpass light speed, they could have spread across the galaxy long ago. Yet the skies remain silent. This silence is at the heart of the Fermi paradox. One possibility is that faster-than-light travel is truly impossible, a barrier never to be crossed. Another is that civilizations capable of such feats choose to remain hidden, guided by caution or secrecy. Perhaps superluminal travel is dangerous, destabilizing spacetime itself, and those who attempt it vanish before they can spread. Or perhaps they dwell in regions of the cosmos already beyond our horizon, unreachable to us until we ourselves break the light barrier. There is also the unsettling thought that we are being deliberately isolated. If advanced beings already move beyond light speed, they may enforce a kind of quarantine, ensuring that emerging civilizations remain confined to their own light cones until ready. The absence of evidence, then, may not be absence at all, but the presence of unseen watchers. Thus, the Fermi paradox becomes not only a question of life, but of speed. If the cosmos contains civilizations who have surpassed the luminous boundary, then their silence is itself an answer, a message hidden within absence. Perhaps we have not yet crossed the threshold, but others already have. And if so, the true question is not whether faster-than-light travel is possible, but whether we are prepared to meet those who already dwell beyond it. In 2015, humanity first detected gravitational waves, ripples in the fabric of spacetime produced by colliding black holes. These waves travel at the speed of light, stretching and compressing reality itself as they pass. But what if faster-than-light travel could be achieved not by riding light, but by riding gravity? Gravitational waves suggest that spacetime can carry information across cosmic distances without matter or energy moving through it in the ordinary sense. Some theorists propose that under extreme conditions, spacetime disturbances could propagate faster than light, carrying not just ripples but entire bubbles of altered reality. If such a mechanism could be harnessed, a ship might surf these waves, crossing vast regions of the cosmos in less time than light would require. More radically, some models suggest that during the earliest moments of the Big Bang, gravitational waves did outrun light. If this occurred once, perhaps it can occur again. Perhaps faster-than-light phenomena are already embedded in the universe's structure, waiting for us to unlock. Harnessing gravity as a medium would not be simple. The energy required to generate gravitational waves is immense, comparable to colliding stars. But natural events already provide them: mergers, explosions, and cataclysms across the cosmos. If a civilization could align with such waves, navigating them like tides, faster-than-light travel might emerge not from breaking rules but from learning to ride the deepest currents of spacetime itself. At first glance, the vacuum of space seems empty, a void stretching endlessly. But quantum mechanics reveals otherwise. The vacuum is alive with activity, particles flickering in and out of existence, fields fluctuating in restless motion. This quantum foam may be more than noise, it may be the hidden architecture of reality. And within it could lie the keys to faster-than-light travel. Some researchers suggest that the vacuum itself could act as a medium, like water or air, with properties we barely understand. If its structure could be manipulated, then spacetime might become pliable, allowing shortcuts or channels where light speed is no longer the ceiling. Already, phenomena like the Casimir effect hint at the vacuum's exotic qualities, producing measurable forces from nothingness. Imagine a vessel equipped to manipulate the vacuum. Instead of pushing against space with rockets or sails, it would sculpt the underlying field, sliding along pathways invisible to ordinary matter. To outside observers, the ship would move faster than light, but within its own frame, no laws would be broken, it would merely be navigating a deeper layer of physics. The vacuum is not emptiness but potential, a restless sea of possibility. If we learn to control it, then faster-than-light travel may not require tearing through barriers or bending space, it may simply mean mastering what was always there, hidden beneath the silence of the stars. Every attempt to imagine faster-than-light travel encounters paradoxes. A ship leaving Earth might arrive at a distant star before it departs, messages could arrive before they are sent, and timelines could fold into loops. Such scenarios appear absurd, but they reveal something profound. Our understanding of reality may itself be incomplete. One resolution is that faster-than-light travel is truly impossible, forbidden to preserve causality. Another is that causality itself is not fundamental, but emergent. Perhaps time does not exist as we perceive it, and paradoxes only seem illogical because we are bound by limited perspective. Beyond light speed, events may not be chained in order, but coexist in a timeless framework. This perspective transforms faster-than-light travel from a question of engineering into a question of ontology. To move beyond light speed is to challenge not only physics but philosophy, to ask what it means for something to happen. If past, present, and future are illusions, then paradoxes dissolve, not because they are prevented, but because they were never contradictions to begin with. Perhaps faster-than-light phenomena, if they exist, are glimpses into this deeper truth. Tachyons, wormholes, warp bubbles, all may be shadows of a reality where time is not a river but a landscape, and light speed is merely one contour within it. To cross the boundary is not only to travel faster, but to awaken to the possibility that reality itself is stranger than any law we know. Long before experiments reveal truths, mathematics often whispers them. Equations can predict realms of reality unseen by human eyes. Relativity itself began as a set of equations, later confirmed by observation. In the same way, mathematics hints at faster-than-light phenomena, even if nature conceals them from us. Solutions to Einstein's field equations, for example, naturally allow for wormholes and warp bubbles. These are not wild inventions, they emerge when mathematics is pushed to its logical extreme. Similarly, certain quantum equations permit particles with imaginary mass, which correspond to tachyons. While these may never exist physically, their presence in mathematics suggests that the framework of physics allows for superluminal domains, even if our universe resists them. Mathematics also predicts paradoxes, warning us of the dangers. Closed time-like curves, loops in spacetime where cause and effect blur, appear as valid solutions to Einstein's equations. Yet their very existence challenges consistency, raising the possibility that mathematics sees further than physical law will permit. The question then becomes, are these mathematical superluminal solutions real glimpses of hidden physics, or mirages, artifacts of pushing equations beyond their valid domain? History shows that mathematics often runs ahead of experiment, and many impossible predictions have later been confirmed. Perhaps faster-than-light travel awaits the same fate. Perhaps the equations are right, and it is only our technology that lags behind. Our universe is not static. It expands, and not gently but relentlessly, driven by dark energy. As it does, more and more galaxies slip beyond the cosmic horizon, carried away faster than light can pursue. Billions of years from now, distant galaxies will vanish entirely, leaving only the remnants of our local group visible. This raises a startling possibility. The natural fate of the universe is to become a place where faster-than-light separation is the rule, not the exception. Already, most galaxies are beyond reach, not by velocity but by expansion. The further the future unfolds, the more profound this separation becomes. In time, even the faint whispers of the cosmic microwave background will fade, and observers will live in apparent isolation, unaware of the vast cosmos that once surrounded them. If faster-than-light travel is impossible, then this is the ultimate fate, eternal confinement within shrinking islands of visibility. But if it is possible, then the future changes entirely. Civilizations could resist cosmic isolation, leaping beyond horizons, preserving contact across an ever-expanding sea. Faster-than-light travel, in this sense, is not merely a dream of exploration, it is survival against the entropy of the cosmos itself. Thus, the universe itself drives us toward the question. Expansion forces us to confront the limit of light speed not as curiosity, but as destiny. Either we remain bound to shrinking horizons, or we find a way to surpass them. Beyond light speed may lie not only discovery, but the only path to eternity. Beyond its scientific implications, the light speed barrier casts a psychological shadow. It defines the limits of imagination. We look at distant stars and know they are unreachable in a human lifetime. We gaze at galaxies and realize their light left long before our species arose. The speed of light is not only a law, it is a reminder of our cosmic smallness. This has shaped our culture, our art, and our sense of meaning. The impossibility of faster-than-light travel makes the stars symbols of longing rather than destinations. Yet at the same time, it fuels our dreams. The very presence of a limit ignites curiosity about what lies beyond. Without barriers, there is no wonder; with them, imagination soars. If faster-than-light travel were achieved, the psychological impact would be profound. The universe would cease to feel vast and untouchable. The stars would no longer be eternal mysteries but reachable neighbors. Entire philosophies would change, religions would adapt, and cultures would redefine themselves. The human story, confined for so long to one planet and one light cone, would expand into something truly cosmic. The psychological horizon is as real as the physical one. To contemplate surpassing light speed is not only to dream of ships and engines, but to dream of new identities, new cultures, new ways of seeing ourselves. Beyond light speed lies not only physics, but transformation of the human spirit. Every serious proposal for faster-than-light travel collides with a single, merciless barrier: energy. The scale of power required dwarfs imagination. To push even a small craft close to light speed demands energy comparable to that of entire nations, and to sustain warp bubbles or stable wormholes may require mass energy on the scale of stars. This creates what some physicists call the energy economy of the impossible. Faster-than-light travel is not forbidden in theory, but the cost may be so immense as to render it inaccessible. The problem is not only acquiring energy, but controlling it. Storing antimatter in sufficient quantities, generating negative energy densities, or manipulating quantum vacuums all involve technologies that push engineering to its very limits. Yet history warns us against declaring impossibility too soon. What once required the energy of empires can now be achieved by handheld devices. Nuclear reactions, once unthinkable, now power cities. It is possible that future civilizations may harness energy sources we cannot yet imagine, tapping black holes, manipulating stellar fusion directly, or extracting energy from dark matter. Thus, the challenge of energy is both obstacle and invitation. It forces us to ask not only whether faster-than-light travel is physically possible, but whether energy itself has layers we do not yet understand. If the universe conceals hidden reservoirs of power, then perhaps the impossible may one day become routine. The key may not be breaking laws, but learning to draw from the deepest wells of reality itself. Across human history, cultures have imagined beings and forces unbound by distance. Norse mythology spoke of Bifrost, the rainbow bridge linking realms in an instant. Hindu epics describe deities crossing universes in moments. Greek gods traverse the sky with effortless speed, their chariots outrunning the dawn. Even ancient shamans envisioned spirits journeying through cosmic realms beyond the pace of light. These myths reveal a universal desire to transcend the barrier of separation. Before physics named the speed of light, imagination had already sensed its boundary and sought ways to leap beyond it. The tales of gods, heroes, and spirits reflect early attempts to grapple with the enormity of space and time, wrapping mystery in story. Modern science fiction continues this tradition, reimagining faster-than-light travel as warp drives, hyperspace lanes, and wormhole gateways. Each story builds on the same impulse, to reject confinement and embrace boundless exploration. These narratives shape our collective psyche, preparing us for the possibility that one day myth might become method. When viewed this way, faster-than-light travel is not only a scientific puzzle but a cultural constant. It reflects something fundamental about intelligence itself. The refusal to accept limits without question. Myths whisper what equations later attempt to prove, that beyond light speed lies not only distance, but destiny. One of the most unsettling consequences of faster-than-light travel is the possibility of time loops, closed circuits in spacetime where events repeat endlessly. Such loops, permitted by certain solutions in relativity, create scenarios where cause and effect collapse into self-sustaining cycles. Imagine a traveler using a superluminal shortcut to arrive before they depart. If they interfere with their own departure, a paradox arises. But relativity suggests another possibility: the paradox resolves by enforcing consistency. The traveler may always arrive, but their actions cannot alter the fact of their departure. In this way, time becomes a loop rather than a line, with events predetermined by their circular structure. These closed time-like curves disturb our sense of freedom. If faster-than-light travel naturally produces them, then free will may be an illusion, trapped within repeating patterns. Worse, they could create cosmic feedback loops, events endlessly replaying themselves, reshaping history into fixed cycles. Some physicists argue that nature forbids such loops through a principle of chronology protection, ensuring that paradoxes never manifest. Others remain uncertain, acknowledging that mathematics allows what logic resists. If superluminal travel does produce time loops, then beyond light speed lies not exploration, but entrapment, a universe where eternity means repetition, and freedom dissolves into necessity. Astronomers speak of a boundary called the particle horizon, the maximum distance from which light has had time to reach us since the universe began. It defines the observable cosmos, enclosing all we can ever see. But beyond this boundary lies the unobservable, a realm hidden not by matter or distance, but by time itself. If faster-than-light travel became possible, the particle horizon would no longer be a cage. We could cross into regions of the universe that remain forever beyond our telescopes. There, the cosmic microwave background may appear different, revealing variations hidden from our perspective. Structures on scales larger than anything we know could emerge, perhaps revealing whether the universe is finite or infinite. Crossing the horizon would also allow us to test one of the greatest mysteries: do the laws of physics truly remain constant everywhere? Or do they vary beyond our reach? If constants like the speed of light or the strength of gravity differ in distant domains, then faster-than-light travel would expose us to realities utterly unlike our own. The particle horizon is a silent wall, drawn not in space but in time. Beyond it lies the untouched majority of the cosmos, regions we may never glimpse without superluminal means. To break the light barrier is to erase that line, turning the unreachable into the reachable, and expanding our universe from what is seen to what truly exists. Many superluminal theories rely on a strange ingredient: exotic matter. Unlike ordinary matter, which has positive energy density, exotic matter would possess negative energy, bending spacetime in ways normal material cannot. It is the key to holding wormholes open, powering warp bubbles, and stabilizing paths that light itself cannot take. Quantum physics hints that such exotic matter may exist in fleeting forms. The Casimir effect, where two plates in a vacuum attract due to quantum fluctuations, can be described as a manifestation of negative energy. Tiny and unstable, these effects cannot yet be scaled, but they prove that negative energy is not impossible, only elusive. Harnessing exotic matter would be revolutionary. It could counteract gravity, repel instead of attract, and curve spacetime into impossible geometries. With it, wormholes might remain stable long enough for traversal, and warp bubbles could be sustained for interstellar journeys. But exotic matter comes with dangers. Its very nature might destabilize spacetime, creating zones of unpredictability where physics itself collapses. If misused, it could tear open horizons or destabilize entire regions of the cosmos. Thus, the search for negative energy is both a dream and a warning. To find it would be to unlock the door beyond light speed, but also to risk unlocking catastrophes greater than we can imagine. Perhaps the most radical possibility is that the speed of light is not truly a fundamental limit at all, but an illusion born of our perspective. Just as ancient navigators once believed the horizon was the edge of the world, we may be mistaking a local phenomenon for a universal truth. Several theories hint at this. In quantum mechanics, entanglement correlations suggest connections that ignore distance. In cosmology, inflation reveals that space itself can expand faster than light. In mathematics, solutions to relativity permit superluminal constructs. Each of these hints at a deeper reality, one in which the speed of light is not a wall, but a property of one layer of physics among many. If this is true, then faster-than-light travel is not about breaking laws, but discovering hidden frameworks. Light speed may simply define motion within our observable spacetime, while deeper strata of reality operate on other principles. Once those strata are understood, the barrier dissolves, not by force, but by insight. The illusion of limits reminds us that boundaries often reveal only the edge of knowledge. To cross beyond light speed may not be to defy the universe, but to finally understand it. And in that understanding, the impossible may become inevitable. The true barrier of light speed may not lie in matter or energy, but in information. Every physical process is, at its core, an exchange of information. Particles collide, waves propagate, signals are sent, all are governed by how quickly information moves. Relativity tells us that light defines the ultimate limit for this transfer. Nothing, it insists, can communicate faster. But quantum mechanics complicates this view. Entangled particles appear to exchange information instantly, correlations existing regardless of distance. Though no usable message can be sent this way, the phenomenon hints that the universe may have layers of information flow hidden beneath the observable. Some theorists speculate that information itself may propagate through channels beyond spacetime, invisible to us yet real. If faster-than-light communication of information were possible, it would reshape everything. We could transmit knowledge across galaxies instantly, building networks that dissolve the meaning of distance. Science itself would transform, as observations could be shared across cosmic scales without delay. At its deepest level, faster-than-light travel is inseparable from faster-than-light information. To move matter across the stars, one must also move signals. Thus, the study of light speed is not only about physics, but about the very flow of meaning through the cosmos. What lies beyond light speed may not only be new worlds, it may be a new definition of reality as information itself. Not all visions of superluminal travel are bright with promise. Some are shadowed with catastrophe. Physics warns that surpassing light speed may unleash destructive consequences, destabilizing not only ships but the very structure of the universe. One danger lies in causality violations. If faster-than-light travel allows events to influence their own causes, paradoxes may proliferate, unraveling the logical consistency of the cosmos. The universe as we know it may not survive such contradictions. Another lies in energy release. Objects pushed beyond light speed could emit infinite radiation, creating destructive shockwaves that devastate everything nearby. The collapse of spacetime is another possibility. Warp bubbles, wormholes, or superluminal fields may be unstable, collapsing violently and tearing open regions of reality. Entire stars or systems could be consumed in the aftermath of a single failed experiment. Even communication carries risks. Faster-than-light signals could create time loops, rewriting history endlessly. Societies might collapse under the weight of contradictions, events shifting without warning as causality reorders itself. Thus, the pursuit of faster-than-light travel is not only a dream but a gamble. To reach beyond the luminous boundary may be to reach into forces too great to control. The promise is vast, but so is the peril. If faster-than-light travel is possible, perhaps the evidence already exists, not in laboratories, but in the universe itself. Strange astronomical phenomena may hint at superluminal processes. Gamma-ray bursts, intense explosions releasing more energy in seconds than stars emit in their lifetimes, seem almost too powerful to explain. Could they be echoes of civilizations attempting superluminal experiments? Fast radio bursts, mysterious millisecond flashes of radio waves, erupt across the sky with energies that baffle astrophysicists. Though natural origins are likely, some speculate that they may be signatures of advanced technologies, perhaps communications or the side effects of faster-than-light propulsion. Even the structure of the cosmos itself may carry signs. The uniformity of the cosmic microwave background suggests early faster-than-light expansion during inflation, smoothing the universe beyond what light alone could achieve. In this sense, superluminal processes are already written into the history of reality. Astronomy, then, becomes not only the study of stars but the search for hints of what lies beyond light speed. Each unexplained phenomenon is a potential clue. Each anomaly is a whisper from the universe, hinting that faster-than-light processes may not be fiction, but fact, waiting for recognition. One provocative idea is that advanced civilizations may already exist beyond the light-speed barrier. If faster-than-light travel is possible, then perhaps some cultures long ago crossed into realms where ordinary physics no longer applies. To us, they would be invisible, unreachable, operating outside the horizon of light itself. These hypothetical pre-light civilizations might have discovered technologies that allow them to step outside spacetime, traveling not between stars but between realities. From their vantage, our universe, bound by the speed of light, might appear primitive, like a child's sandbox. They may observe us without interference, choosing not to reveal themselves, or perhaps they interact subtly through phenomena we cannot explain. Such a hypothesis connects to the Fermi paradox. If the cosmos is ancient and life is common, where are the signs of great empires? One answer is that they are no longer bound by light speed. They have moved beyond, existing in dimensions where our telescopes and detectors cannot see. Their absence in our skies may be the strongest evidence of their transcendence. The idea is speculative, but it raises an unsettling thought. To discover what lies beyond light speed may be to discover not only new physics, but neighbors who left long before us. The barrier may not be empty, it may already be populated. One of the greatest questions about faster-than-light travel is whether reality itself could remain stable if it were achieved. Physics, as we know it, is finely tuned. Laws interlock with precision, preventing paradoxes and maintaining order. But superluminal motion threatens to disrupt that harmony. If faster-than-light travel destabilizes causality, then the fabric of the universe could unravel, leading to contradictions and inconsistencies at every scale. Events might rewrite themselves endlessly, creating a chaotic cosmos without coherence. In such a universe, science itself would collapse, for no experiment could yield reliable results if the past could shift at will. Some physicists argue that this is why faster-than-light travel cannot occur. The universe protects itself through consistency. Just as energy conservation and entropy define the order of reality, chronology protection may serve as a safeguard, ensuring that paradoxes never arise. In this view, light speed is less a barrier and more a defense mechanism, preserving the stability of existence. But others propose that superluminal travel may not destroy stability, but reveal a deeper framework where contradictions dissolve. Perhaps our logic is incomplete, and in higher domains of reality, time loops and reversed causality are not errors but natural order. If so, the universe may remain stable even as it allows what we call impossible. Thus, the question is not only whether faster-than-light travel is possible, but whether the universe can withstand it. Beyond light speed may lie new frontiers, or the collapse of reality itself. The earliest moments of the universe were a crucible of extremes. During inflation, spacetime expanded faster than light, stretching quantum fluctuations into the seeds of galaxies. If this expansion was truly superluminal, then traces of it may still exist as relics, encoded in the cosmic microwave background and the distribution of matter across the universe. These relics are subtle but profound. Tiny variations in the background radiation reveal patterns that no ordinary process could produce. They are the fingerprints of a superluminal past, reminders that the universe itself has already outrun light. If space-time once broke the limit, perhaps it can again. Some cosmologists suggest that inflation never fully ended, that in distant regions, new universes are still being born, expanding faster than light beyond our reach. If true, then faster-than-light phenomena are not rare but fundamental, occurring continuously at the largest scales of existence. We may live in a universe where superluminal expansion is the rule, not the exception, hidden only because we are confined to one bubble among many. Studying these relics offers more than cosmological insight. It provides clues to the mechanisms of faster-than-light processes, perhaps even technologies that mimic the dynamics of inflation on smaller scales. If we can decode the fingerprints of the Big Bang, we may learn how to replicate the universe's greatest trick, breaking the luminous barrier itself. If faster-than-light travel becomes possible, the implications may extend beyond our own cosmos. Theories of the multiverse suggest that our universe is but one bubble among countless others, each with its own physics. The speed of light might act as a boundary that prevents us from slipping across, locking us inside our local reality. But surpassing it could mean more than traveling faster, it could mean escaping into other universes. Some cosmological models propose that black holes may serve as bridges to alternate universes. If a vessel could survive passage beyond the event horizon and somehow exceed light speed relative to our spacetime, it might emerge elsewhere, not in another part of our galaxy, but in a different reality altogether. Wormholes, too, could connect universes, providing true multiversal gateways if stabilized by exotic matter. The possibility is staggering. Entirely new realms could await. Universes where the laws of physics differ, where light speed is slower or faster, where matter behaves in alien ways. Some may be barren voids, others may teem with unimaginable forms of life. To go beyond light speed could be to step outside existence as we know it, exchanging our universe for another. Thus, the light barrier may not simply define the edges of our universe. It may define the edges of all universes. To break it is not only to reach other stars, but perhaps to leave the fabric of this cosmos entirely, venturing into the infinite sea beyond. At present, the universe enforces isolation. Stars are separated by light years, galaxies by millions of light years, and communication between them is throttled by the relentless pace of light. Civilizations, if they exist, are trapped in their own cosmic neighborhoods, unable to share knowledge or culture except across spans of time that make cooperation impossible. Faster-than-light travel changes this forever. With it, isolation dissolves. Civilizations could form galactic networks, sharing information instantly, exchanging travelers across the stars, building communities that span the cosmos. The loneliness of space, the silence that has haunted astronomers since the beginning, would be broken by dialogue. Yet the end of isolation is not without risk. Civilizations may compete, clash, or conquer. Superluminal travel may ignite cosmic wars, where entire star systems fall in moments. The same technology that unites could also divide, magnifying conflict on scales we cannot imagine. Still, the promise of connection is powerful. Faster-than-light travel would not simply expand our map, it would expand our relationships, creating a truly cosmic community. Whether that community is peaceful or violent is uncertain, but one thing is clear: beyond light speed, no world need ever remain alone. Ultimately, the question of what lies beyond light speed is not only physical, it is philosophical. Limits define knowledge. They mark the boundary between what we know and what we cannot yet see. Light speed is the greatest of these limits, a wall standing between us and the greater universe. But history shows that every boundary is temporary. The sound barrier once seemed absolute, until it was broken. The atom was once invisible, until it was split. The stars were once unreachable, until telescopes brought them into view. Light speed may be the grandest barrier yet, but it may follow the same pattern, unbreakable until, one day, it is not. Even if the barrier endures, the pursuit itself reshapes us. To ask what lies beyond light speed is to reach beyond what we are, to confront mystery with imagination. It drives science forward, expands philosophy, and fuels stories that bind cultures together. The search matters as much as the discovery. Perhaps the truth is that beyond light speed lies not a destination, but an expansion of ourselves. Our capacity to dream, to question, to explore. Whether we ever cross the boundary or not, the horizon it creates will forever push us to grow. And in that sense, what lies beyond light speed is already here. It is the endless drive to seek what waits beyond the limits of the known. The speed of light is not just a limit, it is the very scaffolding of reality. It defines how space-time is measured, how distances and durations are calculated, how causality flows. To speak of moving faster than light is not simply to speak of traveling faster, it is to imagine changing the geometry of the universe itself. Space-time is elastic, stretching under expansion, curving near massive objects, rippling with gravitational waves. Yet through all of this, the speed of light remains constant, the metric against which everything else is judged. It is the ruler of rulers, the yardstick of the cosmos. Exceeding it, therefore, is not like outrunning a horse or an arrow. It is like outrunning the very grid that defines distance. To go beyond light speed is to step outside the architecture of space-time, to move in ways that geometry itself cannot describe. Ships, signals, or beings moving superluminally would not follow paths through space-time as we know it. They would trace routes invisible to us, existing in dimensions we cannot chart. This suggests that faster-than-light travel is not merely an extension of current motion, but an entirely new category of existence. Just as quantum physics revealed worlds beyond classical mechanics, superluminal travel may reveal frameworks beyond relativity. To cross the barrier is not to bend the map, it is to redraw it. When discussing faster-than-light travel, we often imagine a single boundary, the speed of light. But in reality, the universe is filled with horizons, each marking its own limit. Black holes create event horizons, beyond which nothing can return. The cosmic horizon hides galaxies forever receding from us. Even quantum mechanics imposes horizons of uncertainty, limiting what we can know. These horizons overlap, forming a labyrinth of barriers. To move beyond light speed would not simply mean crossing one, it might mean crossing many, each with its own consequences. A ship moving superluminally might dodge not only the horizon of light but also the horizons of causality, time, and entropy. Perhaps the universe is layered, each horizon protecting deeper truths. Faster-than-light travel could peel these layers back, revealing new domains of physics step by step. Beyond one horizon lies another, and another still, like cosmic nesting dolls. The pursuit of the superluminal is thus not a single leap but a cascade of discoveries, each boundary breached leading to another more mysterious. In this sense, light speed is the first horizon, but not the last. What lies beyond may not be a final destination, but a series of thresholds, each one testing the courage, intellect, and imagination of those who dare to cross. While physics dominates the discussion of faster-than-light travel, there is another realm equally important: ethics. What responsibility comes with the ability to cross light speed, to travel distances instantly, to communicate across galaxies, to rewrite causality itself? The dangers are immense. A civilization wielding superluminal technology could conquer entire star systems before resistance could form. Weapons traveling faster than light would render defenses meaningless, striking before detection. Even unintended consequences, such as destabilizing spacetime, could harm not just one world but entire galaxies. Yet the opportunities are equally vast. Faster-than-light travel could unite civilizations, spread knowledge, and end isolation. It could prevent extinctions by enabling evacuation from doomed worlds, or allow cooperation across vast distances to solve universal challenges. Thus, the question is not only whether faster-than-light travel is possible, but whether it should be used, and how. Technology on such a scale demands wisdom equal to its power. To master light speed without mastering ethics would be catastrophe. To master both could be transcendence. Beyond light speed lies not only physics but morality, not only possibility but choice. The future will depend not just on whether we can cross the barrier, but on how we decide to use what waits beyond. Entanglement is among the strangest phenomena in physics. Two particles, once connected, remain correlated no matter how far apart they drift. Measure one, and the other reflects the result instantly, as if distance does not exist. To many, this feels like faster-than-light communication, but is it really? According to mainstream interpretation, entanglement does not transmit usable information. The results are correlated, but random, meaning no signal can be sent. Still, the instantaneous nature of the effect raises unsettling questions. If entanglement is not bound by light speed, then perhaps it points to hidden layers of reality where information flows differently. Some physicists propose that entangled particles are not communicating across space but sharing a deeper connection outside space-time. If true, then faster-than-light processes may already exist, woven into the foundations of the quantum world. We simply cannot yet harness them. If entanglement is a clue, then beyond light speed may not require building engines or bending space-time. It may require discovering how to use quantum connections as pathways, opening invisible corridors where information, and perhaps matter, can leap across the universe instantly. The key to superluminal travel may already exist in the smallest scales of nature, hidden in plain sight. When discussing faster-than-light travel, we often assume reality is objective and fixed. But relativity teaches us that perception shapes truth. To one observer, events may unfold in one order; to another, they may unfold differently. Time itself depends on perspective, stretching or shrinking depending on speed and gravity. This raises a profound possibility: perhaps faster-than-light travel is not impossible in absolute terms, but only from our current frame of perception. Another vantage might see what we call impossible as natural. Just as subatomic particles experience time differently, or as light itself moves without aging, perhaps superluminal beings could exist, perceiving reality in ways we cannot imagine. From their perspective, our universe may appear static, frozen in slow motion, every moment already written. They might move across our cosmos like we move across a page, not limited by sequence but able to perceive the whole. To them, light speed may not be a barrier at all, but a trivial rule of a lower dimension. Thus, faster-than-light travel may not simply be about engines or mathematics. It may require altering perception itself, learning to view reality not as a linear sequence but as a complete tapestry. In that view, the boundary dissolves, and the impossible becomes a matter of perspective. The night sky is filled with billions of stars, each a potential cradle for life. Yet the cosmos is silent. We have listened for decades, scanning the heavens for signals, but no voice has answered. This silence deepens the mystery of faster-than-light travel. If it is possible, why has no civilization revealed itself? Perhaps they are already beyond our reach, existing in domains we cannot perceive, having transcended the light-speed barrier. Or perhaps they remained silent deliberately, knowing that superluminal communication could destabilize young civilizations like ours. Another possibility is sobering: faster-than-light travel may be catastrophically dangerous. Civilizations may attempt it, only to destroy themselves, leaving behind no evidence but silence. If so, the stillness of the stars may be a cosmic warning, echoing across galaxies: the path beyond light speed is perilous. Yet silence can also mean opportunity. If no one has yet succeeded, the door remains open for us, or any civilization, to be the first. The lack of signals may not be a warning but an invitation, a chance to explore uncharted realms. The stars remain quiet, but their silence is not empty. It is filled with possibility, with mystery, with the question that drives us: what lies beyond light speed, and why has no one yet answered? Faster-than-light travel belongs to a class of ideas once dismissed as impossible. Yet history shows that the impossible often becomes reality. Heavier-than-air flight, once unthinkable, is now routine. Splitting the atom, once inconceivable, powers our cities. Even the digital age, unimaginable centuries ago, is woven into daily life. The physics of the impossible challenges us to view today's limits as tomorrow's stepping stones. While relativity forbids superluminal motion within spacetime, it also provides mathematical doorways, warp bubbles, wormholes, tachyons, that hint at deeper truths. Quantum mechanics, too, suggests that the universe plays by stranger rules than classical thought allows. Perhaps the ultimate lesson is that impossible is often a word for what we do not yet understand. Light speed may be the greatest example of this, a limit that is not absolute, but conditional, waiting for the right breakthrough. To study it is not to deny physics, but to expand it, embracing the possibility that beyond today's walls lies tomorrow's science. Thus, faster-than-light travel is more than a fantasy. It is a question of timing, of discovery, of learning the hidden rules of reality. The impossible of today may be the inevitable of tomorrow. To imagine faster-than-light travel is to imagine moving not only through space, but through time. Relativity shows us that speed and time are inseparable. As velocity increases, time slows. At light speed, time stops. Beyond it, what happens? Does time reverse, dissolve, or expand into something we cannot yet conceive? Perhaps beyond light speed lies a timeless domain where past and future coexist. A traveler moving superluminally may not see events as a sequence, but as a whole, perceiving the universe as a completed tapestry. This would not merely be travel, it would be transcendence, a step into a reality where time itself is not a boundary but a perspective. Such a journey may be the ultimate goal, not only for exploration but for understanding. For to master faster-than-light travel would be to master time itself, to see beyond beginnings and endings into the deeper truths of existence. The speed of light is thus not only a wall of space, it is the threshold of eternity. From the earliest fires lit in caves to the sails that crossed unknown seas, exploration has defined the story of intelligence. The stars are the ultimate frontier, calling across distances so vast that even light struggles to bridge them. The dream of surpassing light speed is, therefore, not a distraction, but a continuation of this ancient drive. It is destiny written in curiosity. To remain bound to one world, one star, is to stagnate. To reach beyond, even against impossible odds, is to fulfill the deepest impulse of existence, to seek, to know, to expand. Faster-than-light travel represents the purest form of that destiny, the promise that no barrier is final, that no horizon is permanent. If achieved, it would mark not just a technological revolution but a philosophical one. It would mean that the universe itself is open, that no mystery is beyond reach, that the call of the stars can finally be answered. Thus, the pursuit of superluminal travel is not only science, it is identity. It is the destiny of explorers, written in the very fabric of being. As we draw to the end of this journey, one truth becomes clear: the speed of light is more than a number. It is a boundary between the known and the unknown, between what we are and what we might become. It defines the horizon of our sight, the edge of our knowledge, the structure of our time. And yet, it also inspires. Every boundary invites challenge, every horizon beckons us forward. To ask what lies beyond light speed is to embrace the unknown, to reach beyond fear into discovery. Whether faster-than-light travel is possible or not, the very act of asking expands our vision, pushing us closer to truths we have not yet imagined. Perhaps we will one day step across this final horizon. Perhaps we will never cross it. But in either case, the question itself shapes us. For in striving toward the impossible, we discover what is truly possible, and in seeking the infinite, we discover ourselves. The universe is vast beyond measure, filled with wonders both seen and unseen. The speed of light defines our reach, holding us within a cosmic bubble. But it also points outward, whispering of greater realms beyond its luminous edge. We have explored theories, from tachyons to wormholes, from warp drives to quantum entanglement. We have faced paradoxes of time, threats of catastrophe, and glimpses of multiversal gateways. Each idea stretches imagination, blurring the line between science and dream. Yet all share one theme: the barrier of light speed is not the end. It is the beginning of the greatest question we can ask. What lies beyond light speed? Perhaps new universes. Perhaps timeless domains. Perhaps truths we cannot yet describe. Whatever waits, the pursuit itself defines us. It is the pursuit of explorers, of thinkers, of dreamers who look at the stars and see not distance, but invitation. And so, as our journey closes, we leave with one certainty: the story does not end here. The cosmos is vast, the questions endless, the horizons eternal. Beyond light speed lies mystery, and beyond mystery lies discovery.